Metacomp Technologies presents CFD++, solving complex multiphysics problems with the most powerful, commercially available computational fluid dynamics software suite. This product overview of CFD++ will consist of 6 sections. We begin with an introduction that will hopefully pique your interest to learn more about the software. Next, we take a look under the hood at the company background and history, including development details of CFD++. This will be followed by areas of applications where we will look at specific examples highlighting key features and capabilities. Then we will see how CFD++ is validated and verified, especially in terms of its accuracy, efficacy, and practicality. We will showcase how users can interface with the software and with our company. And finally, we will demonstrate how CFD++ is integrated into the complete Metacomp multiphysics workflow. CFD++ is Metacomp's flagship simulation software designed to solve comprehensive fluid dynamics problems with accuracy, robustness, and speed. It consistently outperforms other commercial solvers in blind benchmarks and workshops. You may be surprised to learn that on a daily basis, CFD++ is running on hundreds of thousands of processors and in over 300 discerning organizations worldwide. To understand why the use of CFD++ is so ubiquitous, we must first look under the hood to see what makes the software so powerful. It's important to note that CFD++ is not a newcomer into this field. As Metacomp's flagship software, it is actually the 7th-generation state-of-the-art solver developed by the founders. Engineers in the computational physics space all over the world are switching to CFD++ to solve their toughest problems. But why are all of these users making the switch? Because Metacomp's core principles are simplifying complexities and reimagining computational multiphysics, making CFD++ the obvious choice for users' engineering needs. Key members of the Metacomp development team have been pioneering computer-aided engineering research and development for over 50 years in both academia and industry, the foundations of which are built on an in-depth knowledge of complex physics and numerical methods in diverse technical areas. A commitment to accuracy, reliability, generality, and speed has been the cornerstone of CFD++ development since its inception. However, our belief is that Metacomp's true success lies in our customer-first philosophy, where user experience is paramount. To achieve this, we live by the principles of learn, do, and serve on a daily basis. With these founding principles as our bedrock, we are able to produce the only commercial solver that can provide efficient solutions to most physics problem classes without sacrificing accuracy or robustness. But what is the secret sauce that allows CFD++ to accomplish these challenging, often contradictory goals? It comes down to a strong, extensible, and general algorithmic framework which is based on a unique unified grid, physics, and computing philosophy. A unified treatment of grid, physics, and computing provides the generality and comprehensiveness for CFD++ to be the one-stop shop when it comes to computational multiphysics problems. No matter the flow complexity, grid type, and computing platform, one single solver can handle it all. Unified grid means that the treatment of different cell shapes and grid topologies is generalized. A single solver becomes equally applicable to all cell types: hexahedral, tetrahedral, polyhedral, and any combination thereof. In addition, the handling of various grid types, structured, unstructured, and non-aligned grid topologies, such as overset grids, is also universal. A unified treatment of physics means the flexibility to solve many types of flows within the same solver. A single computational framework is used to solve incompressible flows all the way to hypersonic. With additional phenomena such as multiphase, conjugate heat transfer, radiation, rigid body dynamics with moving meshes, reacting flows, compressible liquids, and thermal non-equilibrium effects that can be added to the mix. Flows can be turbulent, transitional, or laminar, steady or unsteady. If there is a complexity to the physics, it can be added and solved all within one solver. Within the unified physics framework are advanced numerical treatments of flow physics. Density and pressure-based solvers are available for appropriate regimes. A multidimensional higher-order TVD interpolation is used to avoid spurious numerical oscillations, while approximate Riemann solvers can guarantee correct signal propagation of inviscid terms. Advanced convergence acceleration techniques are employed through unique preconditioning, relaxation, and multi-grid algorithms. In essence, these treatments help ensure the accuracy and efficacy of the computations, so CFD is not just colorful fluid dynamics, but reliable computational solutions to real-world problems. Unified computing allows both Linux and Windows operating systems to be supported, with total portability between different computing platforms. Single and multi-core processing capabilities are available, with a variety of parallel processing MPI flavors and interconnects, enabling scaling to a very large number of cores. Metacomp is actively porting CFD++ to GPGPUs and should have versions running on such platforms in the very near future. CFD++ is a powerful tool for solving fluid flow problems, making it a reliable choice across numerous engineering applications. Engineers in aerospace, turbomachinery, automotive, marine, and power industries have successfully leveraged its capabilities to tackle complex fluid dynamics problems with accuracy and efficiency. External aerodynamics applications can range from flows over full-scale commercial aircrafts to automotive vehicles. Helicopters can be simulated with models for the rotors or with fully transient mesh motion. Complex physics such as store separation and icing can be incorporated into each application. In the high Mach and altitude regime, advanced numerics with high-temperature gas dynamics can help handle ballistic and re-entry applications. Internal flow applications can range from large-scale gas and liquid turbines with complex moving geometries to smaller biomedical devices and injectors. Multiphase cases can involve free surface tracking for tank sloshing and marine applications, or cavitation modeling over a propeller blade. How can our software handle such a wide range of applications? Because the unified philosophy enables diverse capabilities within a single solver, everything is tailored to the nature of the problem, ensuring adaptability and efficiency across various engineering problems. Fluids can be compressible or incompressible, influencing their behavior in various systems. Different types, such as ideal gases, real gases, barotropic fluids, and supercritical fluids, require tailored equations of state to model their thermodynamic and flow characteristics. Ideal gases follow simplified equations like the ideal gas law, while supercritical fluids need more complex equations of state. Fluid flow may involve chemical reactions, such as combustion in engines or processes in reactors, adding further complexity to simulations. At high temperatures, thermal non-equilibrium effects must be considered. Many engineering applications involve multiphase flows and phase change phenomena like condensation, evaporation, or solidification, requiring special models for interface dynamics and heat transfer. The ability to efficiently model chemically reacting flows plays a crucial role in CFD by enabling the accurate simulation of processes where chemical reactions and fluid motion interact. CFD++ features a generalized Arrhenius chemistry model supported by a comprehensive built-in database of species properties for both gases and liquids. Its smart integrator dynamically determines the required steps for accurate chemistry inversion, enhancing both precision and convergence. A Chemkin conversion tool for species and reaction information is available. Users can define their own finite-rate chemistry through a customizable interface, enabling tailored simulations. The software efficiently detects and processes reactions with non-integer powers, ensuring robust computational handling. Various models are available to simulate pressure-dependent reactions, expanding the range of chemically driven flow analyses. An equilibrium chemistry module is available to directly compute the chemical equilibrium state of a given mixture without requiring the specification of any reactions. A flamelit table feature allows for faster simulations with the same fuel oxidizer condition. Reaction source terms are also read from the flamelit lookup table. A dynamically thickened flame model can be used for turbulent combustion to resolve flame fronts and capture turbulence chemistry interactions. A volumetric source feature can be used to simulate an ignition source. Supercritical combustion is handled via cubic or user-defined tabulated equations of state. Subcritical liquid fuel can be simulated using the EDP, mixture, or FEEM model, including the modeling of phase changes. Atmospheric reentry can be accurately simulated with models of dissociation, ionization, and vibrational relaxation, and special wall models are available to account for the effects of ablation and catalytic recombination. CFD++ has proven highly effective in simulating combustion processes in both rocket and air-breathing engines. Our software offers many features that enable the modeling of high-speed mixing and combustion, such as in scramjets, where rapid fuel-air interaction is critical. Additionally, it can simulate supersonic nozzle flows, incorporating liquid droplets or solid particles to capture complex fluid dynamics. Detonation-based flows, including pulse detonation and rotating detonation engines, exhibit extreme pressure and temperature variations that require precise computational modeling. The deflagration to detonation transition remains a key focus in combustion physics, significantly influencing propulsion system efficiency and performance. The thermal non-equilibrium module enhances hypersonic CFD simulations by precisely capturing thermochemical non-equilibrium effects. A two-temperature model solves an additional equation to account for energy relaxation between different temperature modes. This approach significantly enhances the accuracy of hypersonic CFD simulations by precisely capturing thermochemical non-equilibrium effects, leading to improved predictions of heat transfer, temperature distributions, and chemical reactions within the flow field. Alternatively, Tanhill curve fits provide an efficient method for computing equilibrium air at high temperatures. CFD++ includes a comprehensive high-temperature species properties database, covering species relevant to Earth reentry, Mars entry, and ablation processes. Additionally, several ionized air transport property models can be employed to refine viscosity and thermal conductivity estimations at elevated temperatures. Special boundary conditions, such as catalytic, ablative, and slip walls, further enhance these simulations. These advanced modeling techniques have been successfully applied to aerothermal heating analysis of hypersonic and re-entry vehicles operating at extreme Mach numbers and altitudes. Several models in CFD++ can be used to solve multiphase flows depending on the physics that needs to be simulated. For mixed or dispersed phase flows, CFD++ offers both Eulerian dispersed phase (EDP) and Lagrangian dispersed phase (LDP) models to simulate multiphase systems where particles are carried by the continuous phase. These models are best suited for scenarios where secondary phases maintain relatively low volume fractions across the flow domain. Additionally, CFD++ includes a full Eulerian-Eulerian model, or FEEM, and a mixture model. For immiscible and free surface flows, a volume of fluid model provides a robust solution, with certain applications potentially benefiting from FEEM and the mixture model. The EDP capabilities in CFD++ are powerful and versatile. This multi-phase framework features various models to simulate special physics for phase change and droplet dynamics, coupling the dispersed and continuous phases. Additional quantities can be tracked for the dispersed phase, such as number density and melting fraction. Various source terms can be computed for the dispersed phase, including lift force and virtual mass effects. Melting, solidification, and particle radiation can be modeled. The Grace model can be used for situations where air bubbles begin to deform and become elliptical. The oxygen transfer model can simulate oxygen mass transfer between bubbles and liquids. Evaporation and condensation models can simulate condensation in combustion products and pure steam flows. EDP is also well suited for ISIN simulations and incorporates a range of features designed to accurately capture the complex physics involved. The aerodynamic breakup model simulates the secondary fragmentation of droplets, contributing to improved icing predictions. Additionally, the supercooled large droplet, or SLD, model accounts for droplet wall interactions, including rebound and splash effects for droplets exceeding 50 microns. SLD modeling plays a crucial role in refining collection efficiency estimates, a key parameter in ice accretion calculations. A Langmuir distribution wizard can be used to automatically configure multiple droplet bins, allowing for realistic simulations of typical icing conditions. CFD++ features a rime ice accretion model and can be coupled with software such as the NASA Lewis Ice Accretion Model, or LEW-ICE, for glaze ice accretion. In the FEEM model, as in the EDP model, separate mass, momentum, and energy equations are solved for each phase. However, unlike the EDP model, FEEM incorporates a volume fraction conservation equation across all phases, eliminating the high volume fraction restrictions present in EDP. Its capabilities include modeling interphasic and body forces, as well as mass and energy transfer processes, such as evaporation and condensation. Interface sharpening is achieved through large-scale interface detection and artificial compression techniques. Additionally, the solution of the number density equation enables the inclusion of coalescence, breakup, and bubble expansion and compression models. Specialized wall boundary conditions are available to accommodate specific scenarios, ensuring accurate and flexible simulations. The Lagrangian dispersed phase, or LDP model, offers a range of capabilities, including several primary and secondary breakup models. It supports simulations involving multiple parcel injections, coaxial in cross-stream configurations, spray angle variations, and variable parcel velocities. The mixture model in CFD++ introduces an additional equation to solve for the volume fraction. In the homogeneous mixture model, relative motion between phases is precluded. Small droplets and bubbles can be handled by the model. It also supports phase change phenomena such as evaporation, condensation, and cavitation, with several Rayleigh-Plesset-type cavitation models available. The non-homogeneous mixture model, on the other hand, accounts for drift velocity between phases, while the effect of turbulence dispersion can also be incorporated for enhanced accuracy. The volume of fluid model in CFD++ is designed to simulate distinct, non-mixed phases, such as gas-liquid interfaces, with artificial compression techniques available for sharper interface representation. It can account for surface tension effects and includes a specialized gravity wave inflow boundary condition for prescribing waves at air-water interfaces, as well as a wall adhesion model to predict wetting angles. The volume of fluid model has been successfully applied to various scenarios, including sloshing, ditching, and boat flows. CFD++ supports both steady and unsteady simulations across a wide range of flow regimes, from low speed to supersonic and hypersonic. Simulations can incorporate heat transfer and radiation effects, with source terms available to enable the inclusion of various additional physical phenomena. A comprehensive set of turbulence models ensures accurate representation of turbulent flow, and a diverse array of boundary conditions accommodates almost all simulation scenarios. Conjugate heat transfer simulations are essential for accurately modeling heat transfer between solid and fluid domains, particularly in engineering applications where thermal interactions play a critical role. In CHT simulations, fluid dynamic equations govern the behavior of fluid regions, while heat conduction equations are solved in adjacent solid domains. A thermal balance condition is enforced at fluid-solid interfaces to ensure accurate heat exchange modeling. CFD++ also includes a solids-only mode for specialized applications. Additionally,
A loosely coupled mode can be utilized for simulations involving significantly different heat transfer timescales. Our software supports isotropic and constant material properties, as well as composite and variable properties, including temperature-dependent characteristics, enabling precise thermal analysis across diverse engineering scenarios. CFD++ offers two radiation models, the P1 model and the discrete ordnance model. In the DO model, the angular space is discretized, solving radiative heat transfer within each computational element. Both models are fully integrated with fluid simulations and conjugate heat transfer, ensuring accurate thermal predictions. Radiation modeling is also available within the EDP framework to simulate particle radiation. CFD++ also supports radiation boundary conditions for enhanced flexibility in heat transfer simulations.
In CFD simulations, source terms can represent momentum forces and heat sources. There are an extensive set of physics source term models in CFD++ for simulating various applications and phenomena, including rotors, porous media, mass injection, stator blades, swirl, and sinusoidal body forces. There are specific models for various flow control devices, such as the jet doublet for active flow control, vortex generators, and plasma actuators. CFD++ offers several simulation methodologies for modeling rotors and propellers, providing both simplified and high-fidelity approaches. The actuator disk model serves as an efficient first approximation, applying a pressure jump and swirl velocity to represent rotor effects. For more detailed simulations, the rotor model, based on the blade element method, enables accurate representation of helicopters and propellers. Blade airfoil characteristics can be defined using both Mach and Reynolds numbers, while rotor trimming adjustments can be made based on pitch or RPM. Correction terms account for hub and tip losses, as well as the effects of rotation, blade twist, and centrifugal pumping. Higher fidelity transient moving mesh simulations, which require explicit meshing of the blades, can be performed to capture intricate flow interactions with rotating components. Turbulence modeling is a crucial aspect of CFD simulations because turbulent flows are prevalent in nature and most engineering applications. The most common approach to simulating turbulent flow involves solving the Rand's equations using classical, statistically steady turbulence closures. All Metacomp developed in-house turbulence models are topography parameter-free models, making them especially effective for simulations involving compliant boundaries or bodies in relative motion. Additionally, most traditional, well-established models from the literature are also available in CFD++. The RT and SA1 equation models are available, along with their QCR and RC extensions, accounting for normal stress and isotropy and rotation curvature effects, respectively. In the two-equation model class, the realizable and cubic K-epsilon models, the SST model, and the nonlinear Helston model are included. CFD++ also features the three-equation realizable K-epsilon RT model, the four-equation Langtry-Mentor transition model, and a seven-equation realizable second moment closure. All models can be used together with a sophisticated wall function treatment if coarse grids are placed adjacent to walls. Higher fidelity predictions are achievable through the use of large eddy simulation, which can be critical for real-world applications involving strongly non-equilibrium flow, massively separated wake flows, and flow over high-lift devices operating near stall. CFD++ has several approaches to make LES practical and affordable. These methods include wall-modeled LES and hybrid RANS LES, such as LNS, and various flavors of DDES, including DDES with advanced shielding functions. Our software is designed to handle a diverse array of topologies encountered in real-world applications, offering specialized modules such as rigid body dynamics and mesh morphing. Its Adjont module enables efficient sensitivity analysis, while mesh adaptation enhances and refines computational meshes for improved accuracy. CFD++ incorporates advanced numerical algorithms that effectively manage low-quality meshes, ensuring robust simulations across a wide range of scenarios. CFD++ offers a range of powerful capabilities for simulating both steady and unsteady flows over complex geometries. It supports simulations with sliding and overset meshes, providing flexibility in handling dynamic configurations. Its sequential cutting approach enables multi-step cutting and blanking, making it a versatile tool for various engineering applications. Both global and body frame motion modes can be utilized. Additionally, CFD++ features an integrated rigid body dynamics capability with a 6-degree of freedom model that accurately computes body motion influenced by forces and moments from the surrounding flow field, as well as external forces like gravity. Co-simulation is also supported in 6-DoF mode, further enhancing its adaptability for advanced simulations. CFD++ allows mesh motion, including relative movement between points, using both analytical methods and radial basis function mesh morphing. Available analytical approaches include a flexible disk model and a piston pump model, providing versatile solutions for these applications. RBF mesh morphing can be implemented through file-based specification or direct application to a boundary. Parallel mesh morphing significantly accelerates transient simulations involving morphing. The Adjont method provides a powerful and efficient way to compute gradients in optimization problems, enabling the development of complex models and improved designs. The Adjont module in CFD++ enables users to efficiently assess how changes in input parameters impact a wide range of outputs or objectives, rather than requiring a full recalculation of the flow solution for each input modification. A single Adjont solution suffices for each objective. This approach is especially effective when analyzing the influence of multiple parameters on a single objective, significantly reducing computational effort. CFD++'s Adjont module offers the analysis of simple and complex sensitivities, as well as shape sensitivities. Shape optimization can be performed for both parameterized geometry and freeform cases. Colorful pictures are nice, but accurate solutions are better. Which is why it's good to know that verification and validation are critical aspects of CFD++ development. Our numerical methods, physics models, and validation cases are well published and cited in highly regarded technical journals and conferences. CFD++ also consistently outperforms other commercial solvers in blind benchmarks and workshops. We are not afraid of scrutiny and challenges, because not only are we confident of CFD++'s abilities, but we feel it is only through exposure that we learn how to improve and understand the needs of our customers. CFD++ capabilities and applications have been published in a variety of well-regarded technical and scientific journals. A comprehensive list of publications can be found on the official Metacomp website. CFD++ has also been extensively validated for a wide spectrum of applications and problem classes. A large repository of validation case documents are available through the official Metacomp website as well. Metacomp Technologies participates in technical workshops annually, where it consistently outperforms other commercial solvers. At the 7th Drag Prediction Workshop, we can see NASA CRM's shock-induced separation on the variation of lift and pitching moment with increasing angle of attack at transonic conditions. At the 6th Propulsion Aerodynamics workshop, CFD++ was able to capture a mixed compression intake with an internal shock structure, incorporating porous bleed regions and vortex generators. The mesh for this case was generated using Metacomp's own general-purpose mesh generation software, MIME. To help with solving challenging technical problems, CFD++ and Metacomp have two interfaces to help. In Advanced User Interface, also known as the AUI, and interfacing with our highly regarded technical support team. The Advanced User Interface provides a guided problem setup process that is both intuitive and powerful. The user-friendly experience can simplify even the most complex and challenging computational physics problems. Specialized wizards are available to automate the setup for specific problem classes. The setup incorporates best practice knowledge gained from years of experience and deep theoretical background. As an example, the turbomachinery wizard automatically sets up the initial and boundary conditions along with the numerical and post-processing settings specific to turbomachinery problems. In cases with high-temperature gas dynamics, such as high Mach re-entry flows, thermal and chemical non-equilibrium phenomena become significant. For this problem class, the thermal non-equilibrium wizard will simplify the setup of the physics, chemistry, and numerics. The Advanced User Interface also provides a consistent experience across the entire Metacomp software suite, with the same guided, intelligent, and intuitive workflow available for mesh generation or a fluid structure interaction problem as it is for computational fluid dynamics. At Metacomp Technologies, we pride ourselves on providing unparalleled levels of technical support. Our engagement with users is not only expected to be insightful and productive, but also timely. Our most important resource is our customers. We've only succeeded in our mission if we can help our customers succeed in theirs. Users will be able to communicate directly with a highly knowledgeable support staff, who themselves will have direct access to the entire Metacomp Technologies development team. Metacomp support offices in the USA, India, and Sweden will help ensure that responses are timely based on your region of the world. Customers are also invited to symposiums that are hosted every 2 years. Here they can interact directly with staff and other users, while also participating in technical presentations, demonstrations, and hands-on training. While CFD++ is Metacomp's flagship software, it is, however, not the only software that we develop. Metacomp Technologies offers a suite of software to accommodate a fully realized multi-physics problem, and CFD++ is able to couple with all of them to form a fully integrated multi-physics workflow. From geometry to mesh to complex solutions involving fluid dynamics, acoustics, and fluid thermal structure interaction. Sim++ can prepare geometries from numerous sources from mesh generation in MIME, and MIME, in turn, can generate meshes tailored for CFD++ applications. MIME is also used in conjunction with CFD++ for mesh adaptation, generating optimal meshes for specific physics applications efficiently. With CSM++ and Meta-FSI, complex fluid thermal structural analysis can be performed with relative ease using CFD++. And CAA++ can be used with CFD++ to perform computational aeroacoustics computations. Thank you for joining us in our exploration of Metacomp Technologies and CFD++. If you would like to learn more about the other products in Metacomp's comprehensive multi-physics software suite, please click on the corresponding link below. Also, please feel free to visit the official Metacomp Technologies website or contact us directly at info@metacomptech.com for more information.